So let's see the scenarios of resource allocation graph. Okay, so this but in case one, we'll try to find a cycle. Okay, we'll try to find a cycle. If there is no cycle, we can say that there is no deadlock. Okay, so let's see graph with no deadlock. Graph with no deadlock. Let's see the edges P1. So it is P1 to R1. Okay, and R1 to P2. R1 to P2, and next P2 to R3, R3 to P3, R3 to P3. But you can see that there is P1 is acquired R2, and this is not a cycle. Okay, there is no cycle here. Okay, and remember that the hold and wait condition is not satisfied here, because P3 is not holding anything but waiting for R3, waiting for R3. There are multiple resources are there. If you look at this particular thing, there is no cycle here. Okay, there is no cycle here. Okay, so if there is no cycle, then then there will be no deadlock. Okay, so here there is no cycle, we can confirm that there is no deadlock. But let's see next case 2, a graph with a cycle and deadlock. Okay, now how this particular cycle is formed. So P2 is held by, sorry, R2 is held by P1. So this instance is done. Then P1 is requesting R2. R2 has only one instance, but this instance is also not free. Okay, so this is held by P2. Okay, so P2 is requesting, P2 is holding R1 and requesting for R3. Okay, but there is only one instance of R3, and this instance is also not free, that is held by P3. Okay, and P3 is not executing anything, it is waiting for R2. Okay, but R2 there is one more instance, this instance is taken by P2. Now you look at here, there is no resource that is free. Okay, there is no resource that is free. There is a cycle. Where is that particular cycle? The cycle comes from here. See, if you look at here, there is no instance that is free. There is no instance, resource instance that is free instances, and this R4 is free, but no process is requesting for R4. Okay, now look at, there is a cycle R2 to P1, P1 to R1, R1 to P2, P2 to R3, R3 to P3, P3 to again R2. The arrows comes to one at the same location, that is where it was started, that is R2. So there is a cycle. Okay, and there is no free instances are there. So, and every process is waiting for, holding one instance, one resource, and waiting for one resource, holding for one resource and waiting for one, holding a resource and waiting a resource. Definitely there is a deadlock. Okay, let's see from P4, sorry, R2. Okay, so R2 is held by P1, so this instance is taken. Okay, so R2 is taken by P1, and P1 is waiting for R1. P1 is waiting for R1, and R1 there is no resource that is free. Currently it is not free. Okay, currently it is not free, but one instance is taken for P3. So there is a, from R1 there is P3. Okay, and P3 is holding a resource and waiting for R2, waiting for R2, and there is one resource that is here which is taken by P4. Okay, so I found a cycle here. I found a cycle here, but not all the processes are holding and waiting for this one. P2 is not waiting for anything, as well as P4 is also not waiting for anything. Okay, these P2 and P4 are not waiting for anything. At some particular point of time, P2 will finish its work and leaves this particular resource. Okay, release this particular resource. So this resource is given to P1. This resource is given to P1, and this requested will be cancelled, and this will be given to P1. Okay, so P1, now P1 is holding R2 and R1. P1 will finish the work. P1 will finish the work, and similar after finishing P1. Okay, P1 will release R1 and R2. So one instance of R2 is free. Okay. Otherwise, P4 will finish the work and release one instance of R2 that will be taken by P3. Now P3, okay, will hold R3, R2. Okay. So there is a cycle, but not all the processes are holding and waiting other resources. So after use of P2 and after the use of P4, they release R1 and R2, which will be taken by P1 and P3. Okay. So the system is not in deadlock. So resource allocation graph is suitable only when the system with one resource and one instance. One resource has one instance. Okay, each resource type has only one instance. If each resource type has multiple instances are there, then this resource allocation graph is failed to say that if the system is in deadlock or not. That may or may not be in a. The next topic is methods for handling deadlock. There are several methods that can handle deadlocks. The first method we are going to discuss is deadlock prevention. Okay, so in that deadlock prevention, it provides a set of methods to ensure that at least one of the necessary condition that cannot be hold. Okay, so there are four conditions that occurs deadlocks. Necessary condition that occur deadlocks. All four must have to be occur. If any one of the condition fails, then there is no deadlock. So similarly here in deadlock prevention, it will give some methods. Okay, it will provide some set of methods. Okay, that can fail at least one particular condition. Okay, but the first condition that we here is mutual exclusion. Okay, so we need to remember one thing, that we cannot prevent deadlocks by denying this particular mutual exclusion condition. Mutual exclusion must be hold when there is there you are using resources, that is, okay, multiple processes are sharing the resources. You must and should use mutual exclusion condition. Okay, you cannot deny mutual exclusion in order to avoid deadlocks, because if you avoid deadlocks, okay, by denying this mutual exclusion, there is one more problem called inconsistency or incorrectness of data. Inconsistency or incorrectness, or you will get incorrect data. Okay, so we need to get correct data. Okay, so and consistent data. So if you fail this particular mutual exclusion, deny mutual exclusion, your data will be inconsistent or incorrect. Okay, but there are some devices which are by default mutual exclusion. Okay, what is that? One, mutex locks. Second, printer. Let's take the example of printer. Okay, so there is only one printer. There is only one printer that is used by two processes, P0 and P1. Okay, what P0 will do? P0 is printing A to Z, and P1 is printing, process P1 is printing 1 to 100. Okay, so printer has to be taken by P0 first, then on and print the entire data, then come to print P1. Okay, otherwise if you try to print P0 and P1 simultaneously, then in that particular paper that you put it on the printer, in that particular paper, the line 1 may contains ABCD, then line 2 contains 1 2 3 4 5, line 3 contains FGHIJ, line 4 contains 6 7 8 9, and so on. Okay, so this is not correct. It is to print all the alphabets in one page, then all the numbers in other page. Okay, but if you uh, simultaneously use this particular printer P0 and P1, the printing will be incorrect. Okay, we cannot give printer simultaneously to both the process. This is by default mutual exclusion. Okay, similarly read only files, because we are not modifying anything, so they also don't get involved in the deadlock. Next, hold and wait condition. We can break this particular condition by using two protocols. First one, if each process can request the resources and be allocated all its resources before it begins its execution. That means, let us take an example. There is a file in your DVD drive and you need to copy it onto hard disk, then take print on the printout. Take print on the printout. Okay. So before your execution is started, you need to request all these resources, that is one, and DVD drive 1, hard disk 2, and printer 3. Okay, all the resources you must have to request before your execution is started, that is this one. Okay, so even though you take printout at the end, you need to request the printer at the start. Okay, then protocol number 2, if you already requested some particular resources and you want some additional resources, in that particular case you need to release all the resources. Okay, that is called, a process can be allowed to request resources only when it has none. That means initially you have DVD and hard disk, you copied into your hard disk, then you need to release both DVD and hard disk. So if you want to take printer, okay, you need to you want printer, you need to release both DVD as well as hard disk. And after releasing, then you request again for hard disk and printer. Okay, hard disk and printer. So in this particular time, if some other process px or py in the queue for hard disk, okay, for hard disk, then this particular process p0 has to wait px py pz, and then it can use again the hard disk. Okay, hard disk and printer will be taken later. This results in a low resource utilization, and if a process needs multiple resources, okay, they have to wait for indefinite amount of time. Okay, the next condition is no preemption. So to break the no preemption, we need to convert no preemption to preemption. Okay, so how this will be done? If a process is holding some resources and requesting another resources that cannot be immediately allocated to it, then it release all its currently holding resources. Okay, then again request for the additional resources. Okay, what is mean by that? If p is total resources are r1 r2 r3 r4 r5, r1 r2 r3 is given to p0, r4 is given to p1, r5 is given to p2. Okay, now if p0 request for r4, then R1, R2, R3, all these three are released. Okay, all these three are first released, then request for all the resources R1, R2, R3, R4, then only P0 will be restarted. Okay, the restart condition of this one is to release all the currently holding resources, then restart your process again only after you get R1, R2, R3 and R4. Okay, so this condition is used for CPU registers and memory locations, but you cannot use this particular no preemption condition for semaphores and mutex logs. Okay, that will lead to again starvation and low resource utilization. So next one is breaking circular wait. In circular wait, each process request the resources in the increasing order of enumeration. That means all the resources are given to some particular integer value, tape drive 1, disk drive 5, and printer 11, scanner 11, printer 12, and etc. So assume that P0 is holding 1, 5, 12 tape drive, disk, and printer, and it need after some time it needs scanner. It needs scanner. So what it has to do, because scanner is 11, this will be 11. Okay, so the order is not correct, it is not increasing order. After 12, 11 is not order. So what it has to do, this particular process has to release 1, 5, 12 and ask for 11, that is scanner, so that 1, 5, 11, 12 will be allocated to P0. Okay, so this is how allocated to P0. Okay, so this is how we can break the circular wait. Okay, so